Now we will talk about second part of this lecture, which is about Ampere's law. So as I told you before, Ampere's law in magnetism, that's what replaced Gauss's law in electric field. What it states, if you have a distribution of current carrying wire, so this current will generate a magnetic field B. If you take a closed loop, so any closed loop, we call it Amperian loop. If you calculate the circulation of the magnetic field along this loop, of B, that's the integral of B scalar dl. dl is the element length along this loop. So if you calculate B scalar dl and you integrate that or you sum that along the loop, the result will be proportional to the current passing through the loop or traversing the loop. Mathematical form, we write a closed integral, like we did for Gauss's law, a closed integral of scalar product between magnetic field B and the element dl or ds, the same thing. That's equal to what? Permeability times the current enclosed. What we mean by the current enclosed? The algebraic sum of all current circulating inside the loop or traversing this surface inside the Amperian loop. Okay? The current that are enclosed, that's I1 and I2, I3 is not inside this loop, so we will not count it. Now, how we calculate that? Is that just I1 plus I2? Because we have I1 out of the board, I2 into the board. So how we will decide the sign of this? So we will be using what other hand rule. Okay? So you take a loop to choose a path, a closed path, but you choose also a direction. This direction, that's the direction of integration. That's the direction of disintegration. I go from this point and I come back counterclockwise here, for example. So you put your hand, your finger pointing in direction of integration, and you will see that your thumb, well, your thumb is out of the page. So any current that out of the page will be counted positive. Any current that is in opposite direction of your thumb, it will be counted negative. So basically, here what we will get, that's equal to what? Mu 0, that's just proportionality factor. I enclosed, what is it? I will go for I1 because it's out of the board, it's in same direction of my thumb. I2 is opposite direction of my thumb, so I do minus I2. And so that's what we call Ampere's law. Here in this figure we see a parallel between Ampere's law and Gauss's law. So they look like quite similar. There is a closed integration, there is a closed loop here, there is a closed surface here. So here what we call a Gaussian surface. Integral along a surface of what? The scalar product between the electric field and the area vector. Here we have circulation of B. What is it? That's the closed integral along a loop, the scalar product between B and the element length, ds. That's proportional to the current traversing the surface that is created by the loop, because this loop will create a surface inside. Any current passing through this surface will be counted in this I enclosed. However, here the surface will enclose what? Will enclose the volume. So any charge inside this volume, it will be counted in this Q enclosed. All right, so let's use this Ampere's law to calculate magnetic field. Similar way when we use Gauss's law to calculate electric field. So let's start with the simplest thing that we know the result, that's an infinite long straight wire. So an infinitely long straight wire, and we want a B outside. Why outside? Because we will calculate this time using Ampere's law the B inside the wire, the magnetic field inside the wire, which is not easily measured. Let's prove this formula using Ampere's law. All right, so what we have here, we have this current, this wire, that's a wire. The current in the wire is pointing out of the page because I'm looking from the top, let's say. So that's the cross section. I choose is a circle. Circle concentric with the wire. So it's the center of this Ampere's loop, that's the center, that's the axe of symmetry of this wire, of the cylindrical wire. So B is tangent to the Ampere's loop. Okay, B is tangent, and DS is tangent. Angle between them, there's just theta equals 0. So the scalar product, what is it? There's just integral B ds. Most of the time in Ampere's law, that's what the circulation is equal to. Nu 0, I enclosed. So just let me write it like that. Well, what is I enclosed? I enclosed by the Amperial loop. Which current I have? I have just current I. Okay, so that just nu 0 times I. Well, we can argue also by symmetry. You know, Ampere's law, like Gauss's law, we use it when there is a high symmetry, object with high symmetry. So we can argue that B here and B here, that's the same thing. That's symmetry of revolution. So if I change this point with this point, nothing changed to the problem. So basically B is constant on the loop, so it can go out from the integral. So this is just B integral of ds. And what is the integral of ds? That's circumference of the circle. So that's B 2 pi r equal nu 0 I, and we get the formula. B equal to nu 0 I over 2 pi r. Okay. All right, very simple, very straightforward. There is no need for integration using Ampere's law. This time I will go inside the wire. I don't care about what's happening outside, I care about what's happening inside. So if I take the cross section of this wire, I zoom it out, I get this. So this, let's say cylindrical wire, it has a radius capital R. And now I am inside this wire. So I take a point inside the wire, so at distance small r, smaller than capital R. So at this point. And I use same way Ampere's loop, which is a circle, concentric with the wire, with cylindrical wire. And for same reason of symmetry, I can write this directly. You need to be confident with that. I can write this directly. B is constant along the Amperian loop, so this is B times the integral of ds. What is the integral of ds? That's just circumference. So this is just 2 pi r. That's equal I enclosed. So what I get, B is equal to what? Sorry, there is a nu 0 here. So nu 0 I enclosed over 2 pi r. So here you have a nicely written formula. Okay, so now, can I go further? Well, without any other information, I cannot go further. So what is I enclosed, by the way? That I enclosed, that's I inside the circle. So if I draw the area enclosed by the Amperial loop, that's the area enclosed by the Amperial loop. So I don't need the current I, the total current I need just a portion of it, which is enclosed by the circle of radius small r. How we calculate that? We need to go back to the previous chapter on current and resistance to be able to calculate this kind of current. It's similar to the formula of B outside, just the difference, here we have I enclosed. So what is I enclosed? I enclosed by this area. Well, that's the integral of the current density times dA. Okay. So I need to know the current density distribution. There is a particular case if the current is distributed uniformly. If I have a uniform current, what it means by that? G is equal to what? G is a constant. If G is a constant, well, we know that I enclosed, what is it? That G times the area. If G is constant. Okay? So what we get from that? I enclosed, what is it? That just G times the area. Well, the area is pi small r squared. But what is G as function of current I? Because we know the current I, we know the total current I. Okay? So G, that's the current over the total cross-sectional area. What is the total cross-sectional area? That's pi r squared. So this would give you I r squared over capital R squared. So you take this and you plug it in this formula, and what you will get? You will get this answer shown. So what you will get, let's write it down, let's verify it. P equal mu 0 I r squared over capital R squared, and you have 2 pi r here. You simplify the r's, and it gives you this expression. So here I want to do a recap. We know B outside, we know B inside. So I assume that this is my radius. So what is B outside? That's just mu 0 I over 2 pi r. That's outside. And what is B inside? B in. That's mu 0 I r over 2 pi capital R squared. So how the field will vary inside the wire? Well, it varies. It's proportional to R, so it varies linearly. So that's the field, that's radial distance. So the field varies linearly, increase linearly with R until reaching the field at the surface, okay? And it decreases as function of 1 over R, okay? And what is B at the surface? B at the surface is just mu 0 I over 2 pi capital. All right. So let's move to another example of using Ampere's law, and a very important practical example. So let me come back to the previous slide. That's a field created by an infinitely long wire at a certain distance from this wire. Let's say I want to increase the magnetic field. What I will do? You need to increase the current. Okay? But you know that if you increase too much the current, the wire will burn out. So that's not a practical solution. There is another practical solution to increase B without increasing the current. That's what we call solenoid and toroid. So let's see, what is a solenoid? I take this long wire, and instead of having a straight wire, I will just rub it on itself, like forming a spiral here, forming a spiral. Okay, so that's real solenoid. So we have a lot of turn, we increase the number of turn here. So what it turned out to be the field inside the solenoid. Okay, inside the solenoid region here, what is B? That's mu 0 I, that's the current, times N. What is N? That's the number of turn per unit of length. So if I increase the number of turn, I'm not changing the current, I just increase the number of turn. Instead of having 200 turn, I will have 500 turn. I will increase the magnetic field a lot, and easily, just by creating more turn. Another version of that, so that if you form a solenoid, you have a turn like that in form of a donut, well, you will have what we call a toroid. And here also, if you increase the number of turn, you are increasing the field. Here the difference here that the field is quite uniform here, and here the field is changing with radial distance r. Okay, so these are two options to increase the field without increasing the value of current. All what you do, just you rub more your wire by creating more turn. So the key parameter here is the number of turn per unit of length. So we will use Ampere's law to demonstrate these two formula. So let's start with solenoid. So if you take a real solenoid like this one, and you want to see magnetic field lines, so they look like something like this. So here you have this turn, and what happened? The current, let's say it's coming out of the board here, and it's coming into the board here. And again, the current come out here and come in here, come out here and come in here. So we have this schematic of a solenoid, like assuming that there is a lot of current I coming out and a lot of current I coming in. So that's why we are increasing the magnetic field. It's like we are increasing the current here. It's like we have a different current. It's like we have different wire. In reality, we have just one wire. That's the idea of solenoid. So that's a real solenoid. In a real solenoid, you see that the feed lines, if you are especially in the region in the center here, the feed lines are quite parallel, and the field seems to be uniform here. When you go out, the feed lines are quite, especially if you go away from solenoid a bit, the feed lines are away from each other. Okay, so the field here is weak. The magnetic field is weak. Remember, when magnetic field lines are away from each other, it means that we have a weak field. So here what we draw here is an ideal solenoid. So let's assume this solenoid is very long. You will get something like that. Lines are quite parallel. You have a uniform field here, same B everywhere. And outside B is equal to what? 0. That's an ideal solenoid. Ideal solenoid, B outside 0 and B inside constant, is uniform. So let's take a loop here, square loop. That's an Amperian loop, and let's apply Ampere's law to this loop. We have integral of BDS along the loop, circulation of B from A to B, that we can write it BDS from A to B, plus integral from B to C of the same thing, plus integral from C to D of the same thing, plus integral from D to A of BDS. So there is one integral that's quite easy to calculate. It's indeed 0. If we go from C to D, B is 0. So what is this integral? It's just 0. So we can cancel it. That's 0. If we go from A to B, or from B to C, let's say, I'm going from B to C. So in this part here outside, B is 0. So the circulation of B here is 0. What happened here? So we have ds in this direction, that's ds, and b is in this direction. What is the angle between them? 90 degrees. What is the scalar product? 0. So this is 0, and by the way, this is 0, and by the way, dA, the same thing as BC, that's 0, for the same reason. So we end up by just this integral. Circulation of the field along path AB is uniform. B and ds, they are in the same direction. ds, what is ds here? Is in this direction. So B and ds, they are in the same direction. So this is just integral of BDS. B is uniform, so B go out from the integral. So this is B integral of ds from AB. That's what we call length h. And this is the integral of BDS. What is it? What? Tell me. Ampere's law. That's a new 0. I have a current I. Actually, it's I enclosed. Now, what is the current enclosed? Well, I have just one current in the wire, but this current is coming out of the loop many times. That's the same current in the same wire, but it's coming out many times. How many times? Let's say n times. So this is nu 0 I n equal BH. What is n actually? When the current come out, we are calculating one turn. The second turn, current come out. Third turn, current come out. So this is a number of turn. Number of turn. Number of turn in this space for the length h. So what is B? That's mu 0 I n over h, and that's what we replace with small n in the formula. That's small n. That's the number of turn per unit of length. Okay, so by the end of the day, mu 0 I times n. As simple as that. Okay? What about toroid? So Ampere's loop is shown here in orange. Okay, so we have integral of BDS, that's nu 0 I enclosed. Okay, so for same reason, the field B is, let's say, in this direction. ds is in this direction. They are all tangent to this Amperian loop, which is a circle of radius r. So integral of BDS, that's just integral of BDS. And B is uniform per symmetry, so this is B times 2 pi r equal u 0 I enclosed. And what is I enclosed? I enclosed is here. That's the current enclosed. There is a lot of current coming into the board. How many current? Well, that just depends on the number of turn. So this is just mu 0 I times n. So what is B? That's mu 0 I n over 2 pi r. So we have here number of turn per unit of length. Number of turn, that's n turn. Unit of length is just 2 pi r. That's circumference of the circle. So it's quite similar to the formula of the solenoid. Just the thing is that r is changing here. So the magnetic field is not uniform. All right, so there is one last point. I need to come back to the previous slide to explain you that. Well, here we draw a magnetic field line in this direction. Why is that? How we know this? Okay, so what you need to do here, you see that the current is coming out of the page. So you put your hand, your finger, all your finger are in direction of current. So how they are your finger? They are pointing out of the page, and you follow the turn. So they are pointing out of the page here and coming into the page here. If you do that, if you go from this point to this point, if you sweep your finger from this point to this point, what you will see that your thumb is oriented toward the right. So the thumb gives you the direction of B. Okay, so that's why we know that magnetic field is in this direction. Okay. Okay, so I will stop here. Thank you for watching. See you in my